In this example, we've been asked to determine the three cube roots of minus 8i, express your answers in exponential form and sketch them on an Argand diagram. So the first thing I need to do is express minus 8i in exponential form and then use de Moivre's theorem to find the three cube roots. So I'll start off with writing down the equation, and I'm trying to solve for z here, but I know that z cubed is equal to minus 8i. So to find the exponential form of the right hand side here, I think a quick sketch is a good idea. So on its own Argand diagram here, we've got the real and imaginary axis. 8i has got 0 in the real axis, negative 8 in the imaginary axis, so it's down here, there's negative 8i. From that diagram I can read off the modulus and the argument, and so the distance from the centre is the modulus, we write that down as r, in this case is 8, and the angle, starting over here in the positive r direction, we go anti-clockwise by 90 degrees to get to minus 8i, which is pi on 2, so the angle theta is minus pi on 2. We come back to our formula and write that right hand side in that form, so z cubed in exponential form now is r e to the I theta, which in this case is equal to 8 e to the I. The angle is minus pi on 2, and at this stage here we add in 2k pi. So that says this same complex number will be evaluated with this angle with each multiple of 2 pi. Plus 2 pi, 4 pi, 6 pi, 8 pi, we end up at the same area. So we add that in there for us to get all our cube roots, our three different cube roots. Now we use de Moivre's theorem to find z by itself. So de Moivre's theorem says to find z, we take z cubed and we need to raise that to the power of 1/3. De Moivre's theorem says then we'll raise 8 to the power of 1/3 and we'll multiply the angle, the argument, by 1/3. So 8 raised to the power of 1/3 for starters, we'll just write like that. And our angle e to the I minus pi on 2 plus 2k pi is multiplied by 1/3. So we can simplify that. 8 to the power 1/3 is 2. E to the I, let's multiply through the 1/3 by the negative pi on 2 and the 2k pi. That will give us minus pi on 6 plus 2/3 k pi. That is our general formula for z. We've got it in terms of k at the moment, but we're going to substitute in different k values to find our three cube roots. We always start at k equals 0, so we write that down, k equals 0, and the solution we get for that we'll label z0. So we just write out our exponential form here, letting k is equal to 0, so the angle is easy, in this case minus pi on 6. 2 e to the I minus pi on 6. That's as far as we can simplify that. That's our first solution. We just increase k by 1. The solution we get for that we'll call z1. 2 will be unchanged out the front. E to the I. Now I've got to add two angles together here. K is equal to 1. So let's do an extra step here. This is minus pi on 6 plus 2/3 of pi. So I think to myself, to add these together, common denominator, pi on 6, and 2/3 is the same as 4 on 6. So I've got 1/6 of pi, negative 1/6 of pi, plus 4/6 of pi. Negative 1 plus 4 is 3/6. So this will give me 2 e to the I. Negative 1 plus 4 is 3/6 of pi. And I can also simplify that to give me 2 e to the I pi on 2. 3/6 is of course 1/2. So I have two solutions. My last solution will come from letting k equal 2. We'll substitute k equals 2, call that solution Z2. Again, we'll take a couple of steps to do this. 2e to the I, we're adding minus pi on 6 to, when k is equal to 2, 2 2's are 4 pi on 3, or 4/3 of pi. Again, adding those angles together with a common denominator, we'll have 4/3 is the same as 8/6, multiplying top and bottom by 2. So minus 1/6 plus 8/6 give me 7/6. So this is 7/6 of pi. We need to write our solutions down with the principal argument. Now remember, the principal argument is used if you're in the top half, we use, so in between 0 and pi, we use a positive angle. If your complex number is in the bottom half of the Argand diagram, we use a negative angle and go around in a clockwise direction. Now 7 pi on 6 is the same as 6 pi on 6 plus one more pi on 6. So 7 pi on 6 goes all the way around 1 full pi and then a little bit more. So it's in the bottom half, so we would use a negative angle. Going around 7 pi on 6 in the positive direction, it would be the same as 12 pi on 6 is a full revolution, is the same as coming back minus 5 pi on 6. So to write this complex number with its principal argument, we would say that that is equal to 2e to the I minus 5 pi on 6, or 5/6 of pi. So we now have our three solutions, all expressed with their principal arguments, and so the last thing to do is for us to sketch them on an Argand diagram. Set up two axes, label the diagram. We've got a real axis and the imaginary axis. And we'll just see what our solutions are. So the first solution, a distance of 2 from the origin and an angle of minus pi on 6. So we know that an angle of 0 is here in the positive real axis. Minus pi on 6 is coming around in a clockwise direction. So our first complex number can be drawn in here, and we'll label that Z0. This angle in here we could label minus pi on 6. Our next solution is Z1, is again a distance of 2 from the origin and an angle of pi on 2, which is 90 degrees in the positive direction, so anti-clockwise. We can draw it on the imaginary axis up here. There's Z1. The last angle, the last complex number, Z2, again a distance of 2 from the origin, angled minus 5 pi on 6, which if we were to come around all the way to here is minus 6 pi on 6, so 1 pi on 6 less than that. So the third solution would be down here. We'll label that as Z2, and we might just put in another angle in here. That's also an angle of pi on 6. So we look at the Argand diagram and we see that the three solutions are nice and evenly spaced apart. They're all the same distance from the origin, so it looks like we have answered our question and sketched the three cube roots of minus 8i.